Hey folks, this is our momentum extension video. In this video, you're going to learn about the different types of collisions. You may remember I mentioned that we call collisions where two objects stick together perfectly elastic. In this video, we'll get into why. And by the end of the video, you'll be able to identify the characteristics of the types of collisions. So with that, let's get started. We have three main types of collisions. And we categorize them as elastic collisions, inelastic collisions, and explosions, also called superelastic collisions. So in all three types of collisions, we are going to see that momentum is conserved. So the law of conservation of momentum is true for all of our types of collisions. So I'm going to write that across all three columns. If you're trying to copy this table on your own, you may want to make it a little prettier you might want to center things a little better than I did. So what's the difference between the three then? The difference between the three is whether or not kinetic energy is conserved. So in some collisions, our energy stays as kinetic energy. In others, however, some of that kinetic energy is converted into other types of energy and leaves the system. So while momentum is conserved, kinetic energy specifically is not. So in elastic collisions, kinetic energy is conserved. So our initial kinetic energy, which I will represent as Ki, is equal to our final kinetic energy. And of course, we are looking at the sums of both. So another way to word this is that total kinetic energy remains the same before and after the collisions. In an inelastic collision, our initial kinetic energy is greater than our final kinetic energy. So total kinetic energy decreases. So some energy is lost to the greater, to the wider environment. In an explosion, on the other hand, our initial kinetic energy is less than our final kinetic energy. So we're actually going to gain energy. That is, some work is done on the system, and so its energy will increase. Now, I do want to mention what a perfectly inelastic collision is. And in a perfectly inelastic collision, the two objects stick together. Actually, it may not be two, so I'm going to cross off two. We're just going to say objects stick together. And the maximum kinetic energy is lost. So in a perfectly inelastic collision, we call it perfectly inelastic because we lose as much kinetic energy as possible while maintaining conservation of momentum. So let's look at an example. I throw a bucket of fish off of a boat. So in our before, we have me and a bucket of fish on a boat. And after, we have the bucket of fish moving off in one direction and me and the boat moving off in the other. What type of collision is this? Well, initially, we kind of have no kinetic energy, right? We're standing still on the water. After, however, we're both moving. So I know that then my final kinetic energy is greater than my total initial kinetic energy. Therefore, we must have a superelastic collision, or an explosion if you prefer that word. I like to use the word superelastic collision because I think explosion makes you think of an actual explosion versus just two things moving apart from each other that were initially at rest. So I think explosion can be a little bit of a misleading term. So moving to a second example, two meatballs of mass 1 kilogram collide and move off. The left meatball was initially traveling at 4.5 meters per second right, and the right meatball was initially traveling at 4 meters per second left. After the collision, the left meatball is traveling at a velocity of 1.0 meters per second to the left and the right at a velocity of 0.5 meters per second right. What kind of collision is this? So to figure this out, so first of all, we know it's not a perfectly inelastic collision, and it's probably not an explosion because we don't have two objects at rest that are moving apart from each other after. We know it's not perfectly inelastic because they don't stick together. So that means we either have an elastic collision or a regular, non-perfect, imperfect inelastic collision. And the way to figure out which it is to calculate our initial kinetic energy and our final kinetic energy and see if they're the same as or less than, whether or not they're equal to one another. So with no further ado, let's start by calculating our initial kinetic energy. So that's going to equal the initial kinetic energy of the left meatball plus the initial kinetic energy of the right meatball. So we know that the initial kinetic energy of the left meatball is going to equal 1/2 times its mass times its velocity squared, initial velocity squared, and the same for the right meatball. We can actually move the 1/2 times the mass out of our equation since they both have the same mass. So it's going to be 1/2 times their mass times the sum of our velocities squared. Plugging in numbers, that's going to be 1/2 times 1 times 3.5 squared plus 4.0 squared. And you'll notice I'm not worrying about directions because remember that 1 squared is 1, but -1 squared is also 1. So in our kinetic energy problems, because energy is a scalar, we don't have to worry about direction. And what I'll find when I plug this in is that my initial kinetic energy is about 14 joules. I'm going to go ahead and do the same for my after. So again, I want to find my total final kinetic energy, which is going to be equal to the sum of the kinetic energy of the left meatball plus the kinetic energy of the right meatball. Thus, 1/2 times mass times the final velocity of the left meatball squared plus the final velocity of the right meatball squared because my mass is not changing. And thus, 1/2 times 1 times 1 squared plus 0.5 squared, or 0.625 joules. Thus, my initial kinetic energy is greater than my final kinetic energy. Therefore, and I use that 3 dot to represent those 3 dots in a kind of like triangle shape to represent the word therefore. Therefore, it is an inelastic collision. So again, if you're trying to figure out what kind of collision you have, checking your initial and final kinetic energies is one way to do that. A trick to make that go faster, if your initial velocities are both bigger than your final velocities, the magnitude, not the direction, right? So 3.5 and 4 are larger than 1 and 0.5. So you know that the sum of their squares will also be larger. So hopefully that's helpful for solving some of these problems a little more quickly. So now that you've learned about the different types of collisions, we are ready to talk takeaways. So first of all, momentum is conserved in all collisions. Energy, on the other hand, is only conserved in elastic collisions. It decreases in inelastic collisions and increases in explosions, aka superelastic collisions. And finally, in a perfectly inelastic collision, objects stick together. So with that, you now know about the types of collisions. Go ahead and see if you can practice sorting them on your own. Best of luck and happy solving.